Okay, welcome to our second in our series of R tutorials for generalized linear mixed modeling. Today I'm going to work mostly from the website, the webpage, the book, and kind of bounce back and forth between there and R because there's some nice stuff on here that I think it's important to see. So mainly what the agenda is to show you or remind you, some of you that already know R, how the ordinary linear regression interface works in R, and also going to introduce you to the package that accompanies Dr. Faraway's book that we'll be using. It is a great book and a great package, and so for this today's tutorial, you'll need to load that package, and if you haven't installed it yet, remember, anything you need to install, you can either type install packages at the console. Whoops, see, now here's a great example of if you can maybe guess what I got wrong here. This is a great teachable moment. Ask yourself for a second, why did what I just typed not work? I'll give you like a second, or you can pause it. All right, so I'm going to show you why. The command is not install.package, it's install.packages. So again, this is something that's going to happen to you a lot. It happens to me. I'm working too fast, I forget the S. All right, there we go. So now it's thinking, and you're probably used to this now. Everything's downloaded and we're good. Now, if I didn't want to do it that way, again, I could go to the packages pane, click install, and type faraway there, which, if you'll notice, just sends the same command to the console. Right? And anytime you install a package that you already have, so I already have it, what it does is it actually updates it. And if you are curious, there is an update button over here. So if I click on that, I see that there are quite many packages that need updating. So it's a good idea to kind of just do this every once in a while. You can select all. If there's sometimes you might not want to update. I'm not going to do this now because this will take a while, and the more packages you have, the longer it'll take. But it's good to do every once in a while. Make sure you're up to date because things do change. Sometimes stuff breaks, or when R updates, sometimes a package needs to be updated. So just word to the wise there. So back here, what the kind of main point of this is to introduce you to the formula interface in R. And so you're going to see this a lot because this is how regression models are fit, is it makes it super easy to indicate what's your dependent variable or your outcome, what are your predictors or your independent variables, and what is your data set, where are you pulling them from. And unlike last time, you don't have to use that selection operator. You don't have to use the $ all the time. You can just type the variable names. The caveat is they've got to be spelled correctly the same way that they appear in your data set. So starting today, for the next few tutorials, what I try to do is, instead of the onerous process of loading data into R, the nice thing about a lot of R packages, including those that are written along with textbooks, is they include data. So the data that we're going to use today actually is already on your computer in the package, and it's super easy to get, so I'm going to show you that. Okay. So some things to read through here are, sort of all the arithmetic operators that you can use in this formula interface. So the formula interface, you actually already used it in the last tutorial when doing X tabs. It's that little tilde. So I'm going to explain a little bit more of how that works today. Mostly you're going to see the plus sign and the star in there, but you can do other things, like you can transform a variable inside the formula interface instead of doing it in your data frame. It's very, very flexible. It's become like a really important part of sort of the R ecosystem. So for this tutorial, we're going to use the teenage gambling data that's in the faraway package. And for any data set that's in a package, and I'll show you this, you can type here's another thing. Let's show you an error that's going to happen. Teen gam. Okay. Now, it couldn't find it. Why couldn't it find it? because I have not done this very important thing, which is that I have not run the command to actually load the faraway package. So it doesn't know what that is because it doesn't have access to it. So now when I type teen gam, it actually knows that it exists, and I can type tab to complete the typing there and press enter. And anytime you type a question mark, so I could type a question mark for summary, which is another command. Anytime you type a question mark and then the command or function right after it, it opens the help pane. So it's just a quick way to get to the help rather than having to do there. And then you'll also may have noticed that the help pane has a backwards and forwards button. So I can press the back button and we're back to the teenage gambling data set. So all data sets that are loaded with packages have a little help page, tells you what the variables are, and sometimes what study it's from. So this is actually a study, came out in the Journal of Gambling Behavior, 47 teenagers survey. It's probably a subset of the data set. I have not seen the paper, but survey was conducted to study teenage gambling in Britain. So we've got sex coded as 0 for male, 1 for female, socioeconomic status as status, income is pounds per week, verbal score out of words. So this would be kind of like an IQ or verbal fluency measure. And then their expenditure on gambling in pounds per year. Now, you might be wondering, well, where is this data set? Well, there's a couple of ways you can get to it. In a little bit, you'll see it pop up. But if you want to make it pop up, the first thing you can do is just type the data set name. And there it is. Right now, for giant data sets, that's not really that helpful. So what you can also do is type data, the data command, and then type the data set in there. And what it does is it puts it now in your values. This is a pointer, so that if you want to start using the data set, it's going to start to pop up there, right? So one thing I want to do is to just see what's in it. So the structure command is helpful, right? So, obviously for a very small data set, there's only 47 rows in it. I can get a sense of what's in there just by seeing it at the console, but you don't want to get used to that, especially when you've got big data sets, hundreds of thousands of rows. It's not going to print out. And it also, even more importantly, even with not a lot of rows, if you got a lot of columns, a lot of variables, which is pretty common, you're not going to view them on the screen very nicely. So instead, what you can do is run the struct command, str. So I'll actually copy and paste from my markdown down here so you can see it on the console. Right. So now once I do that, it appears now. So now it's actually here, just like we loaded it in. Notice that struct just kind of gives us the same thing as that the toggle function there. It tells us we've got 5 variables. 2 of them are integers, one's a number, another integer number. We know though that sex is actually numeric codes. So one thing that you might want to do, and actually you won't see this because the way I compiled this file, I had actually done it. So sometimes it's helpful more for the purposes of summary, but if you have a predictor that's really a factor, the numeric codes, you don't want to put the numeric codes in there unless they're coded like this, 0, 1, which is a valid, what we call linear contrast. It's a valid code. If you included this 0, 1 variable in a linear model, it would do what you expected it to do. And I'm actually going to show you the difference. But first, let's make a new factor, so a new variable. And it's always good practice, right? So the variable sex already exists in your data set. So you do not want to create you don't want to change that variable and then paste it over. You want to call it something new. So whenever I make a factor, right, a categorical variable out of a set of numeric codes. I just use the original variable name underscore fac as factor. You'll come up with your own method, but that's a nice cheap way to do it. So now I'm going to copy to clipboard, go over to the console. And as you can see, that adds this new variable. So now if I run str again, it pops up. So this is what you're going to see anytime you have a factor. A factor is special. If you view this SPSS, it's, again, it functions as you might think. The data are stored both as numeric codes, but then as labeled levels, right? So it will tell you how many levels of your factor do you have. So we have 2, male and female. Now, the way I wrote the code is that when you change a variable to a factor, you have to first say, well, what variable do I want to change? The rest of it, you don't have to supply. R will figure it out for itself, but it's really good practice to actually specifically say what you want it to do. So the levels command in factor you're telling R what values exist in the data as they are. So I put down 0 and 1 because that's what currently the sex variable contains. The second part is to say, well, okay, for each time I find one of those levels, 0 and 1, what labels should I map them to, right? So this order matters, right? If we look over in the help, 0 for male, 1 for female. So whatever order your levels are in. So I could flip that around. I could have put 1, 0. I would have to flip this part around. And there's something happens if you do that you might find useful later, but we're not going to discuss it. So again, good practice to when you're creating a factor from a numeric variable in R, use the factor command and always supply the levels and the labels, and remember that the order of the labels must match the order in which the levels are in that command. So now we have a valid, and we can check this because we have a small data set. If I look, I see every time I see a 1, right, I see over here in the fact column that it is indeed female, right, and zeros are males. Okay. So now the fun part, okay? A linear model in R, a regression model, linear regression, is accomplished using the LM command. And again, if you want to see the help page for that, LM, right? This is something that you're going to use all the time. And again, it's one of these functions where there's a ton of default options that you're going to ignore. Basically, all you need when you use LM is the formula, which is how you specify what's in my regression model, what's it doing, and then the data set. And you can scroll down and see some examples down in the bottom. And so we'll run an example now. So what we're going to do, we've converted to factor. I actually want to show you the difference between what the output looks like. If we start so let's say we had not converted to factor, but what we want to do is we want to use the gambling expenditures. So go back to the help page here. Gambling expenditures as our dependent variable, our outcome, and as predictors, the sex of the survey respondent, their socioeconomic status, income, and again, income is pounds per week, and their verbal fluency score. So this is the formula, right? And we kind of think about this as the left-hand side is the outcome or the dependent variable. So we're saying this is my outcome, and you can almost think of the tilde is, right? Gambling is modeled as a function of sex plus status plus income plus verbal. So notice this is linear regression, no interactions, just 1, 2, 3, 4 predictors, all of which are numeric at this point, but that sex codes, basically sex right now as it is is an indicator variable for female, right? Everybody with a 1 is a female, everybody with a 0 is a male. So when I run this regression model, notice, by the way, if I just typed LM, this is another kind of, fun / annoying thing with R. If I just type LM, so fit the model, and by the way, you'll get used to this, formula, comma, where's the data? That's all you need for ordinary linear regression to work. There's other things you can add, but barely do I ever have to use them. So if I just type that, R is going to print out some stuff, but all it's going to do is essentially print out, this is now the fitted regression equation, right? So we would say that the expected value of gambling given the predictors would be the intercept beta 0 minus 22, this is beta 1 times sex, plus 0.052 times status, right? So on and so forth, the way you learned about linear regression. Obviously, there's many important things missing from this output. So in R, what happens is a lot of the times, especially with regression models, you will want to fit the model and then save. There's a bunch of stuff that happens in the background that isn't printed. So when you instead run this command, right, fit this regression model and then save the output to this, whatever you want to call it, so gamb.mod. Now it pops up here, and just so you know, if you're interested, you can click on that, and there are lots of things up here. What you saw before, that's the coefficients, they live there. We've also got the model residuals. We've got the effects, which is sort of like just similar. We've got the rank of the design matrix, the fitted values, QR decomposition, a bunch of other stuff. As well as the data frame, R will copy the data over there. And if there's any missing values, the default is to delete the entire row of the data set. So you can actually see when you look here, so there's no missing data in this data set, but if there were, you could look inside your model objects to see, well, what is the actual data set that was used for the model? So they're the same here. But you're usually not going to have to inspect that, because every linear regression process has a method for the summary function. So again, just to make it easier to see, we'll print it at the console. So you're going to always want to, when you run a linear regression model, you're going to use LM, formula, comma, data set, assign it to a name, an object, it'll pop up there, and then you run summary object. And this is what we're used to seeing, right? So let's walk through what we've got here. So this is always nice dummy check. The first thing it does is bark back at you. It says, well, this is what you asked for, right? You wanted gambling as your dependent variable and then an additive model with these 4 predictors. Yes, that's what I wanted. It gives you a 5-number summary of the residuals. This is kind of a nice way to check. Well, you'll hear about, diagnostic tools here, but what you're looking for is that the median hopefully is close to 0. It's not really great here. Talk about what that means. We'll ignore that for now. Most people are interested in the coefficients. So you get what you think. The estimate column, those are the fitted betas. So that would be sort of the components of your regression equation. Then we've got a standard error for each estimate. If you divide estimate by standard error, you get the t-value that's in the 3rd column. That is compared to a t-distribution with 42 degrees of freedom, and a p-value is computed based on that. So given just an uncritical look at p-values, we might say that sex was a significant predictor, as well as income. and interpreting that, we can see that as sex goes from 0 to 1, remember it's gambling expenditure in pounds per year. The amount of gambling expenditure goes down for the average person by 22, a little bit over 22 pounds. Now think about, what does that mean for a minute? Sex isn't actually a numeric variable. But what happens when I change from 0 to 1? Well, what are the codes, right? Or I go up by 1 unit. Right? The 0 category is male. The 1 category is female. So this coefficient represents the difference between, really the direction matters too. It represents what happens when you change from a male participant to a female participant, or if you look at the difference between males and females participants. So this represents how the estimate changes for females compared to males. So you would interpret this as adjusting for status, income, and verbal score. On average, females' gambling expenditure is below, right, less than 20, so negative 22 they spend less than men by an average of about 22 pounds per year. Income, similarly, controlling for sex, status, and verbal. As your income goes up by 1 pound per week, you can expect about almost a 5 pound per year increase. Other stuff you see down here, we've got the residual standard error, degrees of freedom, which go with the t-tests, a multiple r squared as well as an adjusted r squared. Talk about those different time. And then sometimes it's helpful to have an overall F statistic for the model. We won't use that as much. Right? So that's the basic linear regression interface that you're going to use over and over and over again in R. So one of the reasons I picked this data set, which has a numeric variable that's coded for factor and then changing it to a factor, is I want to show you how this output will look when you use the other version of the sex variable. So that code is right below it. So here I'm going to fit the same model, but now using sex fac rather than sex. And I'm going to summary that model. Now, if we compare, all the numbers will be exactly the same because it is indeed the same model. Right? So if you look down here, can you spot the difference? The difference is now a slightly different coding. So when you have a factor as one of your variables in your regression model, the default is to create dummy variables or indicators. So the default is what's called the default, or what's called the treatment contrast. And you can find out what this means by simply typing contrast teen gam sex fac. So it shows you that because of the way I wrote the factor code, that this variable is actually coded exactly the same way as the numeric variable, right? That it is an indicator for female sex, right? So we see that males get a score of 0 for female sex, right? They're not females. And females get a score of 1 for female sex. So this is still a 0-1 variable. It just looks different. The important thing to note, because this will confuse you later, is that when you have one of these indicator variables in your model, R is going to show you what category goes with the coefficient. So it prints out female because this represents the female indicator variable. Right? In this case, it's very easy to interpret, just as before, right? The beta coefficient, the estimate average gambling in pounds per week. Same as before. It'll get a little bit more tricky when you have multiple categories in one big variable. But it remains the same. Each time what happens is R will automatically create for you a set of indicator variables. And you may already know this, and it's addressed in the book, that in order to make the model work, your set of indicator variables is one less, right, than the total number of categories, because one category is redundant with the rest of them, and so that gets swept into the intercept. So in fact, 22.55, so on and so forth, actually represents the males. Now, it's not the average expenditure for males. It's actually the average expenditure for males with 0 socioeconomic status, 0 income, and 0 verbal. So it actually doesn't make any sense. But if we had taken that out of the model, so if I run another model, GAMFAC2, just with sex, now it makes sense. Now notice the coefficient's a little bit different, but if I was to do psych describe by teenage gamble group teenage sex fac, you'll see, right? The mean for the males, 29.78, mean for the females, 3.87, which would be exactly 25 pounds per year lower, right? So 29.78 minus 3.87 gives you the coefficient here for female in the regression model. So this is to show you that a t-test is actually just a special example of the linear regression model, which you hopefully learned in another class, but just always like to point that out whenever I can. Okay, what else do we want to do? So we checked that out. Right, so you've learned all about confidence intervals, p-values, which one's better, it really depends on what you want. The p-values are printed out, as you can see, for each coefficient when you have when you call the summary on the model object. If you want confidence intervals, you have to ask for them specifically. So it's a little clunky. There are some helper functions for this, but I wanted to kind of show you the default. So the default would be the confint command, confint, which works on pretty much all linear model objects. So type in the model object, gam mod vac. And by default, it uses the 95% confidence level. You can change it. I put it explicitly up there, but if I don't put it in there, these are 95% confidence intervals for all the coefficients. Now this might be confusing because you don't see the coefficients anymore. If you want to see the coefficients along with the confidence intervals, you can use what's called the cbind command, which just kind of creates a data frame on the fly. So what I'm asking for is a way to extract the coefficients from the model is just use the coef function. Let me show you what that does on its own. Coef vac just lists out the coefficients, which is basically the output from the lm command. So now I can wrap those together in a column and put those side by side with the confidence intervals. And now I see, right, this was our regression equation. So for example, the difference between males and females adjusted for the other variables, right? Females spend about 22 pounds per year less. And here's our 95% confidence interval. So notice how wide it is. We're actually still pretty uncertain about what the true magnitude of this difference is. Note that both the lower and the upper limit of the confidence interval are negative numbers, and that is just a kind of a twin a result to the fact that we have a small p-value here. I won't get into that much, but just want to point that out. Right? So again, we interpret confidence intervals not as probability statements, but simply just as confidence statements. So if we, we could say, we're about 95% confident that in the population of British teens that females on average spend anywhere from almost $39 to about pounds, 5.5 pounds less than males. So confidence interval kind of tells you, sort of gives you a little bit more information. Yeah, we think females spend less than males. We're fairly certain that they definitely spend less. We're just not sure exactly how much less. And that's a direct result of the fact that we have a small sample size here, right? Okay. One more piece to add in. Let's compare now whether a model that includes, we might have the hypothesis that really the difference between males and females with respect to gambling expenditure, we may think that actually varies by income, or the other way around. We might think that the relationship between income, which we see as positive, right? The more income you have, the more likely you are to spend a bit on gambling. We might think perhaps maybe that is moderated by sex, or that the linear relationship between income and gambling depends on whether you're a male or a female. So there's two equivalent ways to fit an interaction in a linear model. The simplest one is to use the star. And what the star does is it takes these two variables, make sure that they're both in there as, let me change this. Make sure that they're both in there as main effects, right? And then includes their interaction. So this shorthand is identical to this, right? So the actual interaction, if you wanted to specify an interaction directly, it's the colon, right? So this is the actual variable that represents the interaction between sex and income. When we type this, we're kind of automatically making sure we get this. It's usually better to type this, use the star, because when you have more variables, you can lose track of, do I have everything in there, so on and so forth. So I'm just going to run this top one. You can trust me and you can try it yourself. You'll get the same output. And now we'll run the summary command. Now, interestingly, right, we find that what previously was a relatively robust difference between males and females is essentially evaporated, right? Why is that? Well, we see that income still matters, but now we have a sex by income interaction. So let's work on interpreting this, right? What's going on here, right? Now, remember, this is an interaction between the indicator for female and income. A binary variable interacting with the numeric variable is pretty easy to think about. Okay? What you have to think about is now we're allowing there to be essentially two different linear relationships between income and gambling, right? So two scatter plots or two regression lines. One that represents the slope for males, and the other that represents the slope for females. Okay, so let's work through this. The slope for males is right here. Okay? So what this model is telling us is that for males, income still, as income increases, gambling expenditures increase on the order of 6 pounds per year for each pound per week of income. The interaction is saying that for females, the slope is this number minus this number, right? So now 6.19885 minus 6.4383, it's effectively 0. So what this is actually telling us is that it can go both ways. The difference between males and females really depends on how much income they have, right? The difference in gambling expenditures, or more broadly, right, that really there isn't an overall difference between females and males in terms of gambling expenditures. What it is that income is really only strongly related to gambling expenditures in males. In females, it's essentially flat. For females, the more income they get doesn't really relate to how much they spend on gambling. Now we could graph that. I don't think I have a graph in here, and you'd be able to see that. You basically there's some simple ways that you could see later in different tutorials about graphing and having two different slopes, two different regression lines in the same graph. And what you would find is you'd find one that's positive, right, sloping upwards to the right for males, for all the data points in the scatter plot that were males, and basically essentially sort of a horizontal one that's slightly kind of bending down for females. Okay, last thing is to talk about when, there's two ways to do, well, there's many ways, but two kind of main ways to use p-values for inference in regression models. The first one we already saw, and that's really helpful for numeric variables and also for variables, for categorical variables that are binary, because the t-tests in the regression model tell you everything you need to know. If, however, like let's say instead of a numeric socioeconomic status, we had like low, medium, high. What we would get when we looked at the coefficients of the regression model would be specific comparisons between, say, low and medium and high and medium or something like that. And we'd have tests there, but our hypothesis might just be, is socioeconomic status related to gambling expenditure at all? So one way to do that is with an analysis of variance on regression models. And this is actually done using what's called a likelihood ratio test. And the Faraway book has a really great overview of that. I want to just sort of show you how that works. One thing this is useful for is also in kind of exploring candidate models. So if you weren't sure about the interaction, or if you had a model that did or did not include a categorical variable with many categories, and you didn't want to rely on the t-tests, what you can do is compare the two models using the ANOVA command. Right? Put the models in some order, and then what it does is it looks at the two and it sees if usually what we're interested in is the null hypothesis of this type of test is that the simple model, it fits the data fine. And so the test will give you a small p-value if this candidate model, which is more complex, significantly reduces the sum of squared error. Essentially, this is a test of whether adding, in this case, all we've added here is an interaction between sex and income. This is a test of whether adding sex or income to sex, adding that interaction, this is a test of whether the model fit gets better, right? The residual sum of squares, whether that goes down, whether the sort of remaining variability that's there after the model is fit, does that go down, right? Is there less to explain now because we've added this new thing? And so the answer here is yes, we've got a small p-value, large F. Now, if I look back up at my model output, This is only true of linear regression models, and it's only true if you have numeric by numeric or numeric by binary variable interaction. The test results are the same p-value. In this case, f is simply just t squared. Right? That won't always be the case, and we'll see that in different ways. Maybe you'd like to run this type of test, the f-test, instead of the t-test, on everything in your model. To do that, we use the drop1 command. And this is similar to the output that you might get in SAS or SPSS as the ANOVA table for your linear model. What this does is it does the same thing, but for all possible effects in your data set. So this is a test here, this first one is a test of the model with everything but status, and then this is our test of what happens when we add socioeconomic status. Right? We actually don't do very much better. Here, what happens when we add verbal, or really when we take it away, right? The model gets worse. What happens when we drop this term from the model gets even worse, significantly so. And again, you'll notice that the p-values match there. That's not always going to be the case. But this, again, if we had these are identical, right? Because all of our predictors here use up only 1 degree of freedom. If instead, again, like I said, we had multiple categories, you'll see that these tests are more helpful in those cases. Okay, so yeah, let's just sort of see what happens when you try to check residuals for these models. There'll be a whole week on that, so you can simply just call the plot command on the model. And what it does, if you call it down here, you have to, it's 4 plots, you have to hit return to see each one. So the first one is residual versus fitted. Second one is a QQ plot of residuals. Third one is a little bit more of a fancy residual plot, and same thing with the fourth one. So there'll be another tutorial on what these are. Just spoiler alert, we see a lot of red flags across these plots, so we'll save the why or what I'm seeing for another day, but you might kind of try to think about what's going on there. And then just as a kind of a way to make a naive scatter plot here with the income slope, you can use the plot command. So I'll do this one at a time. So I'll run the plot command first. Okay. So here's our data, gambling expenditures, income. If I want to add the regression line, I take the coefficients from the model, and that becomes my regression line. Now, remember, we just found that this is the overall line. We would find a different line for males versus females. Also, it's probably a good idea to transform one or both of these variables. So just to show you, if instead, a lot of times with income, it's a little bit better to put it on a logarithm scale. We might see it as even more linear. Going to look a little bit different. Now, when I do that, this line isn't going to make any sense. It's no longer on the plot. So in order to get the correct regression slope, I would have to refit the model. But that's just an example of how you can put transformations into your code and it runs smoothly. Okay, so that takes us all the way to the end here. So a lot more detail given to you on the HTML version of this tutorial. So go ahead and consult that, and I'll see you next time.